All right, welcome to this review on probability theory, which is mainly targeted at those that already had some exposure in the past and would like to refresh or even expand a little bit their knowledge. For instance, because they are about to take a course in science or in engineering that requires probability. Before starting, I would like to make a short reflection. Probability theory is a difficult beast, mainly because its foundations are difficult to understand. Uh, Fortunately, in most cases, one doesn't require a deep understanding of the fundamental concepts to apply probability theory in practice. So, for example, one doesn't need a deep understanding of the Lebesgue integration to compute an expectation or to explicitly apply the Radon-Nikodym theorem to compute a conditional PDF. However, there does exist a small subset of those fundamentals that are absolutely essential to be able to apply probability theory in practice without getting confused. This review will put together these essential fundamental concepts and gradually delve into more specifics such as probability distributions and expectations. Our first goal today will be to review what a model is, specifically what a probabilistic model is, and what randomness means. To this end, we need to start by recalling that probability theory is a branch of mathematics, and mathematics is a formal science. Formal sciences are essentially those that are concerned with form rather than with content, and two prominent examples include mathematics and logic. To illustrate this idea, consider the following two examples. If it rains, then it is cloudy. If you call me, then I come. Logic is not concerned with rain or with weather. It is not concerned with telephone calls. It will just identify here the form of these two propositions. That is, A implies B, where A and B are statement variables that act as placeholders or containers for whatever real world meaning we want. Logic will then take abstract propositions and deduce other abstract propositions. When it comes to applying mathematics to solve a real-world problem, we will always be relying on a mathematical model, which is essentially a collection of mathematical objects such as sets, scalars, vectors, matrices, functions, and their relations or constraints among them, typically expressed by means of equations or inequalities. For example, suppose that we wish to analyze a system that comprises two solid bodies connected by one spring. To this end, we can create a model where we identify the mass of the bodies with two scalars, their positions with two functions, and so on. And then we capture the relation among them using the equations dictated by Newton's and Hooke's laws. From this point on, we will not be dealing with masses or springs. We will be manipulating the objects and equations in the model to draw conclusions such as, for example, that k has to be greater than a certain constant k sub 0. These conclusions, interpreted back from a perspective of the real world, give rise to predictions, such as, for example, that we need a spring with a certain strength for a given application. Probability theory deals with a special class of mathematical models called probabilistic models, where real-world situations are abstracted into a set of outcomes. So, for example, all situations where one rolls a die and the upper face contains a single dot is identified with the outcome omega 1, it doesn't matter what what is the color of the die. It doesn't matter who rolls the die. It doesn't matter where it is or the rotation on the horizontal plane. All those details are abstracted away in this step. Remember the meaning of the word to abstract, which means to group together by common features, right? What makes a model probabilistic is that we assign probabilities, which are numbers between 0 and 1, to outcomes, or more specifically, to sets of outcomes, which are called events. The reason is that it's not possible in many situations to assign non-zero probabilities to each individual outcome. As before, what we do in probability theory is to work out the math by manipulating these sets and numbers and elements and so on to draw conclusions, such as, for instance, the probability of other events. If we have done a good job by constructing a model that is faithful to reality, specifically by properly choosing the probabilities so that they reflect accurately the relative frequency or the likelihood of the corresponding events, then the predictions that we obtain by reinterpreting the conclusions from the real-world perspective will be correspondingly faithful to reality. Okay, so although what we have discussed so far looks easy, in my experience, the main source of confusion that people have when applying probability theory is caused by not bearing in mind these boundaries between the real world and the mathematical world. Specifically, note that there's no randomness in the mathematical world. Every conclusion that we draw here is the result of, put it this way, deterministically manipulating sets and probabilities using the properties and equations and definitions that we are about to see. So to dig deeper into what this actually means, let us look into what are the two main ways of handling uncertainty. And to ensure that we don't get confused with all the mysticism surrounding the notion of randomness, we will not be using here coins or dice to illustrate these ideas. Instead, we will be adopting what I think is a more illustrative example. This is a lithium polymer single cell battery with a nominal voltage of 3.7 volts. I have charged it and used it to fly a small drone for a while. I don't know what is the voltage now. One possibility is that I model this voltage as a deterministic unknown quantity. For example, I can assume that is any number in this interval over here. In this way, I'm not saying that some values are more likely than others. I simply don't know. Another possibility is that I model this voltage as a random quantity. For example, by leveraging my prior knowledge about the nominal voltage of this battery and the fact that I haven't used it until complete depletion to model it as a Gaussian random variable with this mean and this variance. In this way, I am sort of quantifying how likely is each value. For instance, those values close to 3.7 are more likely than others. Okay, so I hope that this slide completely dispels the confusion around the meaning of randomness in probability theory. The key message is that randomness is a way of modeling uncertain quantities or events. However, when I ask students what randomness means, I often get answers of the form, it is something that we don't know or something that cannot be predicted. It seems that people tend to think of randomness as something where the laws of cause and effect are violated, or essentially something where the gods roll the dice. However, the existence of this kind of phenomena is, of course, interesting, but is handled by philosophy, religion, theories of free will, and for some even quantum mechanics and so on. But this philosophical meaning of randomness is not what probability theory is about. These are two different concepts with the same word. There's no magic or a mystery in the technical notion of randomness. This should also clarify why, from the lenses of probability theory, we cannot say that a phenomenon is random. What we can say is that we model a phenomenon as random. Indeed, many people assert that there exist phenomena that are intrinsically random. However, when we ask them why, they essentially come up with their own definition of the philosophical notion of randomness that has nothing to do with what we have discussed here. In my view, not being clear about the distinction between the philosophical and technical meaning of the word randomness is the number one source of confusion that people encounter in probability theory. For this reason, if you are going to remember one thing of this video, let it be that randomness is just a way of modeling uncertainty. There's no magic there. For this reason, I think that the key message to remember in this video is that nothing is random from the lenses of probability theory, but we can model events or quantities as random. So now that we have our feet on the ground, we are ready to leave behind the real world and the modeling process to delve into the mathematical world. We will see that from this point on, everything is totally deterministic from a philosophical point of view. Let's start by denoting by omega the sample space, which remember is the set of all outcomes. An event is therefore a subset of omega. This can, of course, include the empty set or even omega itself. A probability measure is a function that takes a set as an input and returns a real number between 0 and 1. The value it returns for an event is called its probability. And to be a probability measure, this function must satisfy these two properties. The probability of the whole sample space must be 1, and the probability of the union of disjoint events must equal the summation of the probabilities of each event. At this point, I recommend that you stop the video and try to prove these four properties out from these two. It takes less than one line in all cases. Now we arrive at the arguably most important and at the same time most confusing concept in probability theory. In fact, when we ask what a random variable is, many people will answer that it is a number that we don't know, or a number that can take multiple values, or things like that. So this confusion arises by not being aware of the boundary between the real world and mathematical world, or between the distinction between the philosophical and technical definitions or notions of randomness. First of all, a random variable is not a number, it is a function. And second, it is called random not because it is random in the philosophical sense. It is random because it is used to model quantities as random. It assigns a real number to each outcome, although it can be generalizable to complex numbers, vectors, matrices, functions, and so on. Put in context of one of our previous examples, there is an assignment between real-world situations and outcomes carried out by the modeling step, and another assignment between outcomes and real numbers performed by a random variable. And we distinguish multiple kinds of random variables. We say that the random variable is discrete when its image, that is the set of all values that it can take, is finite or countable. Remember that a set is countable when we can assign a natural number to each element in a one-to-one fashion. And we say that a random variable is continuous when the probability that it takes a given value is 0. This is confusing for many because they mistake the PDF with the probability, but this is a misconception, as we will see. Notice the notation here. Capital letters denote random variables, so functions, and lowercase is used for real numbers. In the handwritten notation, I use these horizontal bars to emphasize that X is a capital letter. So we have looked at random variable as an assignment from outcomes to real numbers, but we can look at it in the other way around by forming events that group together all outcomes for which the random variable takes a specific value that will partition the entire sample space. We can even go a step further by forming more complicated events that group together outcomes for which the random variable takes values in a given set. And this allows us, given the probability measure, to obtain the probability distribution of a random variable, which is denoted in this way, and it gives us the probability of the event that collects all outcomes for which the random variable takes values in a given set. In this example, this set S is the set of 1 and 2. But providing a distribution in this way is cumbersome, mainly because a probability measure is a function of sets, as we said before. For this reason, we use other functions to specify a distribution. Specifically, one can use the cumulative distribution function, or CDF, which is which provides the probability of the event that x takes values less than a given x, the probability mass function that provides the probability of this event, that x is exactly x, and therefore it can only be used for discrete random variables, and also the probability density function, PDF, also called simply density, which is a function such that the probability of this event, x falling in this set, equals the integral of the PDF over that set. So for this reason, the probability of, for instance, a Gaussian random variable taking a specific value is 0, right? Because this integral would be over a set that contains just a single point, right? So the integral is 0. Two remarks on notation. We are using the same letter to denote the probability mass function and PDF, because there's no confusion, right? This one is used only for discrete random variables, and this one will be used for continuous random variables. And I am not using the bars on the subscripts for clarity, but it must be understood that they are capital letters. At this point, I suggest that you stop the video and review the main properties of these functions. For instance, the CDF is non-decreasing and right continuous, takes values between 0 and 1. This one also takes values between 0 and 1, and the summation of all of them must be 1. The probability density function is non-negative, and its integral over the entire space should be 1, although the function itself can take values greater than 1. You may also want to review the main probability distributions. It is not critical to know the details, but at least knowing which ones are continuous, which ones are discrete, what are their parameters. For instance, the Bernoulli, geometric, binomial, perhaps multinomial, Gaussian, uniform, and high square. That would be a good set of distributions to have a look at. So now we understand what the distribution of a random variable is, and this is certainly the most complete piece of information about a random variable that one can hope for. However, it often occurs that such detailed information is not available, or we would like to condense information about the random variable at hand into numbers that we can interpret or compare. To this end, one can use expectations, which, recall, for a discrete random variable are defined as the weighted sum of the values that the random variable can take, weighted by their probability. This can be written in short in terms of the PMF in this way. For continuous random variables, the definition is the integral counterpart of this expression, where this f is now the PDF. Observe that we have here two definitions of expectations, a private definition for discrete random variables and another one for continuous random variables. It is worth mentioning that both can be put together as the same definition by using the so-called Lebesgue integral, because the summation is just a special case of Lebesgue integral. However, one doesn't need to understand that definition to follow this review. I just mentioned this to point out that the presence of these two definitions doesn't entail a destruction of the beauty and elegance of probability theory. It is just a simplification adopted here and in many courses. Finally, I would like to suggest the following exercise, which is to show that the expectation is equivariant to affine transformations. This is also one line and can be done both for the discrete and continuous cases. All right, so now that we have laid the foundations, let's start to add layers to our probabilistic framework. One of the first extensions we can think of is that of a function of a random variable. Remember that a random variable assigns a real number to each outcome. A function of a random variable will assign a real number to each possible value of the random variable. This effectively adds a layer to our model, right? Remember that from the real world we go into outcomes through this modeling step. Then from the outcome we go into a real number using the first random variable, and then using the function we get another number assigned to the first value. Therefore, it is immediate to recognize that a function of a random variable implicitly assigns a real number to each outcome, and therefore it is implicitly defining a random variable on its own. In this example, it means that instead of going from outcomes to the values of the first random variable and then to the values of the function of the random variable, one can directly think of this random variable as an assignment from each outcome to the values of this function. With this perspective, it's not surprising that one can always find the distribution of z if one is given the distribution of x and, of course, the function g. To see this, consider this example where these are the values of x and these are the values of z. The probability of z taking the value z1 would be, of course, the same as the probability of x being x1, because this is the same, they are associated with the same event, right? And in turn, here we see that this function g assigns the same value z2 to both x2 and x3. In this case, the probability of z equals z2 is of course given by the probability that x equals x2 plus the probability that x equals x3. And the reason for this is that these two outcomes constitute or define disjoint events, right? The bad news here is that sometimes one is unable to find a closed form expression for the PDF of z. So now let's put this together to compute the expectation of a function. It is important to keep in mind that we will not be introducing additional definitions. We will just be relying on the definition of the expectation of a random variable that we already discussed, and the observation that a function of a random variable is also a random variable. With the notation of the previous slide, the expectation of a function g of x can be expressed as the expectation of this random variable z. And by the definition of expectation of a discrete and random variable that we discussed before, this is just this weighted sum over here. Okay, so now to simplify notation a little bit, we will be expressing the summation over all possible values of z in this way rather than in this way. This is just to minimize clutter on this slide. Okay, so the probability that z takes the value little z is, by definition, the one that we provided before, the probability of the event that contains the outcomes that give rise to a value of capital Z equals little z, right? So in this example, the probability that z equals z1 is clearly the probability of the event that contains these two outcomes. Uh, all the other outcomes will give rise to a different value of z, and therefore do not contribute to the probability of z1. Similarly, the probability that z equals z2 is the probability of this event over here. Now let's try to express this event in terms of x rather than in terms of z. In this case, it is easy to see that the event where z equals z1 is the same as the event where x equals x1. In this case over here, we see that the event where z equals z2 is the union of the event where x equals x2 and the event where x equals x3. What we have illustrated in this figure can be mathematically expressed in this way, where the union ranges across all x whose image is the little z at hand. And if we remember the properties of a probability measure that we discussed earlier, the probability of disjoint events equals the sum of the probabilities. And this can be expressed with a simpler notation in this way. Now, substituting this probability here, we come up with this expression. And applying the distributive property, the z comes inside the inner summation. Now one can just recognize that z is equal to g of x, and this double summation over all values of z and all values of x that give rise to that z is essentially the same, or exactly the same, as summation over all values of x. And then we come up with the expression for the expectation of a function. With this derivation, I also tried to illustrate what is the way of thinking in probability theory. Observe that we are not thinking of coins or dice or variables that take values that we don't know or things like that. We are just dealing with sets and functions and mathematical properties. This is, from a philosophical point of view, it's a totally deterministic derivation. Nothing random is here. Okay, so this was the expectation of a function of a discrete random variable. For continuous random variables, the same or similar logic would apply, and one would obtain a similar expression with the probability mass function replaced with the probability density function, and the summation replaced with an integration as always. As a small exercise, you may try to use these expressions to show that scaling a random variable has the impact of scaling its expectation by the same factor, and that the expectation of a constant is the constant itself. Certain expectations of functions of random variables have their own name. This is the case of the variance, which is just the expectation of the square of the random variable minus its mean. As a quick exercise, you may show that the variance of this affine function of x equals the square of the scaling factor times the variance. Adding a constant to a random variable never plays a role in the variance. This is because the mean is cancelled here. You may also want to show that the variance can be equivalently expressed as the expectation of the square minus the square of the expectation. The solution to both exercises is very short, and the second one is provided here for your reference. So now that we are comfortable with one random variable, we can look at what happens when we have multiple random variables. Remember that by definition, a random variable just assigns real numbers to outcomes. So when we have multiple random variables, we just have multiple real numbers assigned to every outcome. In the case where we have just two random variables, x and y, this means that we can identify each outcome with a point in the x-y plane, and this is useful for illustration purposes. As in the case with a single random variable, one can use the probability measure, which is the master function in any probabilistic model, to compute the probability of the event that x and y fall in a given set S. Note that technically speaking, S is not an event because it is not a subset of the sample space, as we said before. It is a subset of R2, right? However, it implicitly defines an event in this way. And the probability distribution will be denoted in the future in this way. Again, specifying a function of a set is not particularly convenient, and for this reason in practice one prefers to use these functions over here, which are straightforward extensions of the functions that we presented for single random variables. As a quick exercise, one can try to show how to obtain the marginal CDF of x given the joint CDF, and similarly the marginal PMF or PDF given the joint PMF or PDF. To solve this exercise, one just needs to use the definitions here and their counterparts for single random variables that we discussed before. A key concept when dealing with multiple random variables is that of independence. We say that two random variables are independent when their joint CDF can be factored as the product of the marginal CDFs, and the same holds for PMFs and PDFs. Note that here I'm explicitly writing the subscripts, and this is for clarity. Whenever there's no possible confusion, I will be omitting them as I did here. This is a common practice in probability theory and statistics to minimize the cluttering when writing math. So note how precise this definition is. Whenever somebody asks us what are independent random variables, the last thing we should do is to answer, no, they are random variables that don't depend on each other or things like that. This is the definition, okay? Now let's look at expectations of functions of multiple random variables. The picture that we need to keep in mind is that each outcome is assigned a real number through each random variable, and then these real numbers are assigned another real number through the function that we are looking at. As with a single random variable, a function of multiple random variables is also implicitly defining a random variable. And therefore, we can just apply the same reasoning as before to obtain the expectations of functions of random variables using the definition for the expectation of a single random variable. One prominent example of the expectation of a function of two random variables is the covariance. The covariance of x and y is defined as the expectation of x minus its mean times y minus its mean, and it generalizes the variance, right? Because the variance of x would be just the covariance of x and x, right? And it is also important to note that the covariance of x and y equals the covariance of y and x, right? Two more exercises here. One is to show that the covariance of x and y equals the expectation of the product minus the product of the expectations, which of course generalizes the expression that we obtained for the variance. The other is that the covariance of this affine function of x and y equals just the scaling factor times the covariance. Again, observe that adding a constant doesn't change the covariance, because we are correcting for the mean in the definition of a covariance. So now we arrive at one of the most important concepts in probability and statistics, which is that of two random variables being uncorrelated. Its importance lies in the fact that it bypasses one of the main limitations of the concept of independence that we discussed earlier. Specifically, to accept that two random variables are independent, one needs access to their joint distribution and check that it factors as the product of the marginals. However, a joint distribution is the most detailed piece of information about a collection of random variables that one can hope for, and therefore it's not surprising that in practice, joint distribution is seldom available. Suppose, for example, that we model the weight and the income of a person as random variables, and we wish to determine whether they are independent. So to this end, we can collect a data set that contains a pair of weight and income for every sampled person. These pairs of values can be identified with points on the 2D plane, as we saw before. If we want to do a good job at estimating the joint PDF, then we need that these points are spread all across the region of the 2D plane where these random variables can take values, and this is unlikely to happen, and also it typically would require a lot of data points. So let's see how we can sidestep this need for knowing the joint PDF. We say that two random variables are uncorrelated when their covariance is 0. So again, please never say, oh, uncorrelated random variables are those that don't have a relation with each other, or things like that. That really causes pain in my ears. This is the absolutely rigorous and precise mathematical definition. Covariance equals 0. And furthermore, it is easy to remember, right? And an equivalent condition is that two random variables are uncorrelated if and only if the expectation of their product equals the product of their expectations. And I leave it as an exercise to show it, which is very simple. And whenever two random variables are independent, they are also necessarily uncorrelated. Another way of saying this is that being uncorrelated is a weaker condition than being independent, or being independent is a stricter or stronger condition than being uncorrelated. One can think of it as the set of independent pairs of random variables being contained in the set of uncorrelated pairs of random variables. The implication can be proven in a single line as presented here, although as always I recommend that you first try on your own. It is remarkable that the converse of this theorem is not true, that is, there are pairs of random variables that are uncorrelated, but they are not independent. So, for example, if x is normal 0, 1, and y is x squared, then it can be easily seen that these two random variables are uncorrelated. As an exercise, you may try to show it. However, an exception is, for instance, when the random variables are jointly Gaussian. If they are jointly Gaussian and they are uncorrelated, then they will also be independent. A similar result can be proven for Bernoulli random variables. I leave this one as an exercise. A simple extension of what we have seen so far is to arrange together random variables to form random vectors or random matrices. And note that we will be denoting random vectors with an underscore and random matrices with a double underscore. And notice as well that expectations act separately on each entry. A prominent example of expectation of a random matrix is the covariance matrix, which is defined as this expectation over here, x minus mu x times its transpose. Similarly, one can define a covariance matrix of two random vectors, possibly of different lengths, in this way. As a quick question, you may think, what is the size of this matrix if you are given the length of these vectors, and if it takes more than 3 seconds to answer, then it's time to stop this video and review urgently matrix algebra. Now we arrive at the last point in our agenda for today, which is that of conditional probability. In a nutshell, conditional probability is about the information that one random variable provides about another random variable. To gain some intuition, consider this example where we have defined two random variables, and suppose that the probability of all events is the same, equal to 1/3. In this case, the probability that y equals 2 is, of course, the probability of this outcome, and this is, as we said before, 1/3. However, if we restrict our attention to those outcomes where x equals 1, it means that we are focusing on just omega 1, and if in this case we wonder what is the probability that y equals 2, we see that y never takes the value 2 for this outcome over here, and therefore its probability, conditional probability, makes sense that it is 0. On the other hand, if we focus on the case where x equals 2, it means that we are focusing on this event, the one that comprises omega 2 and omega 3. And if under this condition we wonder what is the probability that y equals 2, we see that y takes the value of 2 for omega 2, but doesn't take the value 2 for omega 3, right? Therefore, it will, out of these two outcomes, y equals 2 only for one of them. And since both of them have the same probability, it makes sense that the conditional probability is 1/2. Then it makes sense that the probability of one event given another event is equal to the probability of both events simultaneously, normalized by the probability of the event that we are conditioning on. Needless to say that in this expression we can replace y with x, so we would be computing the probability of x being in one set when we know that x is in another set. Those sets, of course, may have some non-empty intersection, otherwise it will be 0, right? Regarding the conditional PDF or PMF, it makes sense that it is given by the joint divided by the marginal of the variable that we are conditioning on. I recommend trying to show that x and y are independent if and only if the conditional PDF is equal to the marginal PDF. So conditioning on y in this case has no effect, it doesn't change the distribution of x. Conditional expectations admit similar expressions to the ones we saw before, with the PMF or PDF respectively replaced with the conditional PMF or conditional PDF. So everything is essentially the same. So in view of what we have said about conditional probability, we can introduce the notion of conditional independence, which is widely used in Bayesian statistics and in machine learning. Specifically, x and y are said to be conditionally independent given z if when conditioning on z, the joint distribution of x and y factors as the product of the distribution of x times the distribution of y. An equivalent condition in terms of the PDF or PMF would be like this. Observe that it is the same as before, but adding a conditioning on z in inside each PDF or PMF. As an exercise, you may try to show that x and y are conditionally independent given z if and only if this expression over here holds, which is just an extension of this expression that we saw before. The solution is here, but again, I encourage you to try first on your own. All right, that was it. I hope that this review was useful for you. The main message I try to convey is that probability theory is a mathematical theory, and therefore it must be approached with mathematical eyes. I find that most people that get confused here do so because they think in terms of dice and coins and gods and magic and things like that. However, you can notice that we managed to present all the definitions and intuition all the way just by relying on sets and functions and equalities and so on. So don't hesitate to come back to this video anytime you find yourself confused. Just to conclude, I would like to say that math is not learned by watching videos, but with a pen and a paper. When you understand all the material here, you must be able to write it on your own without checking any reference or video. As a matter of fact, I guarantee that this is what I did. These are just general definitions and facts used in the everyday life of a researcher in machine learning or statistics. That being said, I wish you good luck in the philosophical sense and all the best.